Hi, I'm happy to share my second mini project with you. This project continues my discussion on the predictability of cryptocurrency in the first project. I did more advanced experiments based on my findings in the first one and fixed some of the problems in my previous machine learning implementation. To begin with, let me briefly review the content of the first project. The specific question I wanted to answer in the first one is, can conventional currencies price information benefits cryptocurrencies price forecasting? I compared the performance of decision tree model and the simple recurrent neural network on predicting the trend of price change of Bitcoin with conventional currencies price information and without. There are mainly three findings in the first project. First, the performance of GRU model on predicting the trend of the price of Bitcoin is better than decision tree model. Second, the overall performances of GRU model and decision tree model are all bad. I did one-step prediction in the first project. For decision tree model, the best accuracy is around 0.54. For GRU, the best accuracy after adjusting threshold is around 0.6. Third, I found after feeding the price information of conventional currencies into GRU model, the model's accuracy increased around 16%. These results drive me to the conclusion that conventional currency market information is useful for cryptocurrency market price prediction. However, there are several problems in the previous experiments. I want to fix some of them in this project. In the first project, I tried decision tree model and GRU model. The conclusion I made based on these two models may not be generalizable to other models. To increase the robustness of my experiments, I tried several new models in this project, including a benchmark model, logistic regression, SVM, random forest, GRU, and LSTM. Second, in the first project, I did one step ahead prediction. I just used a trained model at each time window to predict one new sample outside of the window. Using this strategy, I could only do static evaluation, thus ignored the dynamic of the performance of the models. In other words, I cannot see whether the information from conventional currencies can increase the predictability of Bitcoin price change more and more as time goes on. In this sense, I changed my evaluation strategy somehow. I still use the rolling window evaluation framework, but in this project, in each round, I trained my models using 3 years of daily price data, and then use the trained model to predict Bitcoin's price change in the next 3 months, instead of just predicting price change of the next 1 day. Also, I added more tabulate and visualization methods to my current Python project script to benefit my results evaluation. Third, I identified some bugs in the first project. The first one is about the threshold adjustment. In real practice, it does not make sense to adjust the threshold accordingly to get the best possible accuracy in test samples. The threshold should be preset. Hence, in this project, I fixed the threshold to 0.5. Besides, the model training process was extremely slow in the first project because to tune and evaluate models using rolling window strategy, each model needs to be trained thousands of times. This time I used Ray, a distributed compute framework, to tune the hyperparameters. By using this tool, I am able to run 5 models using 4 CPU and 1 GPU simultaneously. First, I also repeated my experiment on ETH, another type of cryptocurrency. Worth to note that in this project, I also examined whether including cryptocurrencies can benefit the prediction of conventional currencies price change. I used the euro as an example to show that. About the data in this study, in line with Project 1, I transformed our original price prediction task to a binary class prediction, or say classification task. In total, the dataset contains 3339 positive cases and 4335 negative cases. I also used rolling window strategy. However, the time window size was changed to 3 years. The jump step was changed to 10 days, and the prediction step was set to 30 months. no, 3 months, which means after training on each 3-year long window, the predictor will predict the price change of the focal currencies in the next 90 days instead of just 1 day. Considering the performance evaluation criteria of this study, I chose accuracy measure because both false negative and false positive are very important for price change prediction. Next, I will report the results of my experiments on each model. The first one is a benchmark model. It is a moving average model. The model always picks the last label of the training sample as a prediction. For example, in a time window, if the last label of BTC price change is 1, the model will predict everything later of BTC price change as 1. For this model, including conventional currencies information or not does not make any difference. Thus, the performance of them are all equal. This benchmark model can achieve around 0.5 accuracy, 0.2 precision, 0.45 recall in the 3 cases. The 3 plots here show how accuracy of the model changes over time for the 3 cases. The red dots are the performance of model with conventional or cryptocurrencies data. The blue dots are the performance of the model that does not have additional information from the other currency system. The corresponding red and blue line represents the linear trend of the accuracy of the model when using and not using traditional cross-market information. The second model is a logistic regression model. After hyperparameter tuning, I found the model performs best when set penalty to L1, C to 0.1. From the 3 graph, we could see how the performance of the logistic regression model changes with time. For Bitcoin, the performance of the model decreases, while for Ethereum and the Euro prediction, the performance of the model goes up. We can also see from the table that the model's performance is better than the benchmark model. For cryptocurrencies, model without conventional currencies information outperforms model trained with conventional currencies information. But for conventional currency price change prediction, when I involved information of cryptocurrencies price into training, the model performance slightly better. The third model is a support vector machine. The best hyperparameter set for it is RBF kernel gamma equals 100 and C equals 100. In general, the performance of SVM model is better than logistic regression model. We can see an upward trend of the performance of the model with additional information from the other currency market. For example, the first plot for BTC, the upward trend of the red line indicates that the price information from the conventional currency market is providing the model with more and more useful information to predict the price change of Bitcoin. Next is the random forest model. The best hyperparameter set is shown in the slide. I found for cryptocurrency price prediction, the model's performance in general is better than support vector machine. But for Euro price change prediction, SVM performs better. Similar with logistic regression model, random forest model seems learn nothing from conventional currencies price information when predicting the price change of the 2 cryptocurrencies. And specifically for Bitcoin price change prediction, the model's performance slightly decreases over time. This result is in line with logistic regression but against SVM. The next 2 models are deep learning models. After fixing the bugs, I redid my implementation on GRU in the first project. The accuracy of GRU on the task is not better than random forest model. However, the mean recall of GRU model is much stable than previous models. The recall score of previous models on BTC and the EUR prediction is just around 0.1, which means they only predict 10% of actually positive returns positive. Therefore, they are very conservative predictors. Instead, GRU's recall score is much higher. This is one of its advantages. Another strength of GRU model is that the performance of the model in all the 3 cases increases with time. On the contrary, the performance of other models in predicting Bitcoin price trends decreased over time. The last model I tried is a one-layer LSTM model. The best learning rate is 0.002, nose number is 25, and the drop rate is 0.412. The model performs badly in the cases of BTC, but for ETH and EUR price trend prediction, its performance is slightly better than GRU. Nonetheless, it is still lower than the performance of random forest model. Similar with GRU model, the accuracy of LSTM model also increases over time, and it also has a much more stable recall score compared with machine learning models. I mainly have 4 takeaways from this project. First, complicated models does not mean better performance. In my experiment, I found that in average, the random forest model outperforms GRU and LSTM. Second, the cryptocurrency market tends to be a more efficient market than conventional currency market. The evidence is that for all the 6 models, even the benchmark model, the mean accuracy for EUR price prediction is larger than the accuracy for Bitcoin and Ethereum price prediction. The more efficient a market is, the less predictable its price is. Third, conventional market provides little useful information to predict the cryptocurrency's price changing, whereas cryptocurrency market provides some useful information to predict conventional currency's price changing. And fourth, we see a positive linear trend of the performance of the models I tried. These results imply that the predictability of cryptocurrencies as well as conventional currencies price trend are increasing over time. In this sense, the two currency systems at least are being more and more internally connected. That is basically all for my second project. Thank you for your listening.